This is Suvarchala, working as an associate professor, Department of Computer Science and Engineering at Institute of Aeronautical Engineering. In this lecture, I would like to discuss some questions which are given in tutorial question bank for the students of IARE. So, as part of the tutorial question bank, the questions related to SQL query and normalizations will be discussed here. As tutorial question bank consists of three parts. Part A, Part B, most of the questions are related to theoretical questions. Part A is one word short answers, and Part B consists of long answers. Most of them are only understanding level only. So whatever theoretical sessions we discussed previously, those sessions or content of those lectures are enough to answer those questions. And Part C consists of most of the questions are applications. We have to solve some problems by applying the concepts learned in this module actually. That is related to SQL concepts. We have more lectures on SQL as well as normalization also. So first, the first question, write SQL expression for the following queries: sailor, reserves and boat. This is the schema of the relation. And sailor is having sailor ID, sailor name and rating, and as well as age is another attribute. Reserves, boat. So these questions are already discussed by using relational algebra, the previous lecture actually. So find the names of the sailors who have reserved the boat name 103, and find the sailor IDs, sailors who have reserved a red boat, and find the colors of the boats reserved by the sailor and by lubber, and find the names of sailors who have reserved a red boat. For any query, if you would like to answer the query, first we are supposed to identify what are the inputs and what are the output we need and from where the input will be taken. So if we analyze the question, find the names of sailors. Names of the sailors are available in sailor relation. Name, sailor name. And that has to be output. Then what are the constraints to be satisfied? Reserved a boat number 103. So boat ID is 103. So where is the boat ID actually? Boat ID exists in the reserves as well as boat. But we need some association between those two. So for a sailor ID is common in these two, and from boat ID of reserve, if you check if it is 103, the respective sailor names are going to be displayed. That means we need to consider the two relations, sailor and reserves. Why not boat? If you are taking boat, what happens? The sailor and boat doesn't have any relationship. Common ID is not there, or common attribute is not there, which are not related actually. So that's why these two are related. By using these two, we can get the join operation also. So like that, we have to analyze what type of output is required, and to get that output, what are the constraints to be satisfied. To put or satisfy those constraints, what are the input relations to be. So like that, if you consider the first query, find the names of the sailors who have reserved a boat name, boat number or boat ID 103. So we are considering two relations, sailors and reserves. We are renaming them as S and R for convenience sake. So S dot S name or a sailor name we are taking depending upon the attribute name, where S dot SID is equal to R dot SID. This is joining, because more than one relation if you are taking as input, we have to write join operations. So if we are taking n relations in the from option and in the where option, n-1 joins must be introduced so that those relations are going to be get connected actually. So RB is equal to, that is reserved related boat ID is equal to 103. First it joins and it filters boat ID is equal to 103. Only those tuples are going to be taken. From those tuples, not entire set of attributes, only this sailor name is going to be selected. Find the Siler ID of Silers who have reserved a red boat. Siler ID of Silers. So Siler ID of Silers is available in our Siler relation as well as reserve relation also. But what is the constraint here? Who reserved a red color boat? So color of the boat is available in the third relation, boat relation. That means we need both three relations. First relation is Siler ID, color is in the boat. But Siler and boat cannot be joined together because there is no any natural join is to do natural join, no common attribute is available. So these two are connected with the reserves relation. So that's why we need these three. This is for joining these two Siler ID. This is for joining these two. So three relations are joined by using two join operations. From those joined tuples, color is available as red. Only those tuples are going to be considered by us. From those tuples, what are the things to be displayed? Only Siler IDs. So find Siler ID of Silers who have reserved a red boat means Siler ID of reserved. We need not have any Silers relation because our boat and as well as reserves are sufficient. Siler ID, even though available in these two, we can use only Siler ID of year and boat ID of these two join. Color is available. So that's why the first relation can be excluded. Even though you're thinking of three, first relation can be excluded. So select RSID from boats and reserve relations and we will join them by based upon the common attribute BID and color is equal to red. And the third one is going to be next relation. Next relation is find the colors of the boats reserved by the sailor. Sailor name is given here. So colors of the boats. So colors of the boats are available. Please observe here. Colors of the boats are available in the boat relation, but sailor name is available in the sailors relation. Two filtrations are there actually. One is filtration, another one is output we need it. But these two doesn't have any common attributes, so the third relation must be considered by us as a related relation. As a part of that, we are going to discuss here third one. Select B dot color, color out. We have to get the colors of the boats reserved by Mr. Lover. So that's why we will have three relations in this example as based upon the discussion earlier. And three relations means two join conditions are there. One join condition. This is first one join condition to join Siler relation and reserve relation. This is another join condition to join reserve relation and boat relation. So based upon these two join conditions, we will get all three relations are joined on natural join basis. From that, only Siler name is available. The respective tuples are going to be taken. And related tuples, only colors are going to be identified. The colors which are written by you, those colors are going to be identified. Find the names of Silers who have reserved a red boat, same as here, Siler ID and the Siler. Second and fourth are same, but here IDs are displayed, here names are displayed. IDs are displayed, so that's why only two relations are enough, but names are available in the third relation, Siler's relation, so that's why we need here three relations. That is the difference between these two, depending upon the output. Here output is ID in the second query. So ID means by joining two relations is enough for us. But name means third relation name is available. Okay, so in one relation color is available, in another relation name is available to retrieve the data and color is for filtering. But these two are connected with the third relation reserves. So that's why we are using here the third three relations and two join conditions as in case of third one only. Okay. So we'll move to the second query. Second query is also same, which we discussed for relational algebra. We have student, class, enrolled, and faculty, and three queries are there. So what is the first query? Find the distinct names of all juniors. Junior means level. Level is equal to JR. Enrolled in the class taught by first I teach actually. It is a faculty name that comes in. So what we need? So student level is JR. Level means level is existing in our relation. Where is the relation? Level. Level is in the student relation. And They asked distinct student names must be displayed by us. So student names are available here in the student relation only. But what is the condition? Another condition, taught by I teach. So student faculty name is available here. So student and faculty are mandate. But these two must be connected. How these two are connected actually? So faculty ID is connected with the classroom and the student name is connected with the class name actually, tools. So faculty ID can be mapped with here student number is going to be mapping with our student. So four relations are required. Explicitly seems to be two relations, but these two relations cannot be joined because they don't have any common attribute. So we have to consider what are the relationships are associated between these two relations. The relationships associated between these two relations are, one is faculty ID is associated with the class and the class is associated with the respective student member enrolled. So that's why we have from class, from means student class is required, class is read, enroll is a faculty. All four relations are required. Four means the three joint conditions we have written. Here, student and enrolled connected, enrolled and class are connected, class and faculty are connected, faculty name is I teach, and level is June. These two are our normal filter conditions. These three are join condition. One, two, three. Four relations, three joins are must. So first we identified what are the output. We need distinct student names and what are the relations to be considered to take as an input. Then we specified the condition, and also the conditions includes both joint conditions as well as normal condition. The second one is find the age of the oldest student who is either a history major or enrolled in a course taught by tech. Oldest student means more age. So the age is there. So maximum age related student must be identified. So what is the question? So first we have to find out the age of the oldest students. That is maximum of student age. Okay. From student, yes. Where? What are the conditions? Major is equal to history. That is directly. Major is available. Age is available. Student, you are going to output no. So that's why these two are available in the student. So one relation student is initially enough. But another one is there. What is the condition? Second condition. And our student number must be available or must be enrolled for the courses taught by I teach. So first I supposed to find out which are the courses are taught by I teach and whether in that particular courses student number available or not I have to check. So that's why this is the student I am finding enrolled. The courses enrolled by the student as a E.SNUM is the enrolled. So how these student numbers must be displayed? Who are registered for the courses taught by the faculty I teach. So that means enrolled gives, faculty gives faculty name filtration, and the class gives combination or a joining of these two. So that's why three relations are there where enrolled class name is equivalent to the C, that is class of class name, and faculty ID is equivalent to the faculty ID. Two join conditions. So this is join condition 1, join condition 2. And what are the another condition? Faculty name is equal to I teach. So we are instead of using the respective relation names continuously, entire relation names, we are using some names are going to be renamed and those are used actually. So where S major is equal to history, S number is in this respective process actually. So with this I am going to get first this inner query provides us all students, student numbers who registered for the courses taught by I teach by this faculty. So if this history major and the respective student number is or condition either or no, so that's why if student number is false in this group, or major is history, any of these conditions satisfied, the respective students, among those students only maximum age we need to find out. Among those students only the oldest student age, that means maximum age. The next query is find the names of the classes that either meet in particular room number or have 5 or more students enrolled. 5 or more students enrolled means count star. And we need to find out the names of the classes. Name of the classes means C dot name, where it exists from class, as well as classroom is equal to R128. Up to this is simple. Names of the classes that meet in the R128. But another constraint is there, no? Have 5 or more enrolled. 5 or more means enrolled students are number must be greater than or equal to. For that, I need to find out the classes for which the number of enrolled students are more than or equal to 5. For that, we are finding enrolled class name. That is from E, I am finding the classes or class names from enrolled group by E's class name. Having count star is greater than or equal to 5. That means what is the subquery gives? The subquery gives all class names in which at least minimum 5 students are enrolled. Minimum 5 students are enrolled. So this is the subquery. So what we are finding? The classes which are having the classroom in this room number are the classes which are having minimum 5 students. That is falls in this group of results. A subquery is going to be written by us, which is useful to us, so that the another condition. First condition is simple, no problem. A single relation, simple condition is enough, so it's enough. But the second condition needs certain data. Okay, like that we have to find out are able to write our SQL statements. Another question also related to SQL statements. Write SQL expressions for the following relational database: Siler, Reserves, and Boat. And 4 queries are there related to that. Find the age of the youngest Siler for each rating level. Youngest Siler means minimum age. So what we are finding? Select minimum S dot age from Silers. Not all from all. Rating wise we need actually. So group by rating. If we want, we can add like this also. Comma rating also. That means I'll get minimum age and rating level also. For this level, what is the minimum age? Each level and respective minimum age can be outputted. That is valid. Because when we are using group by classes, select statement should contain either group by variables or aggregate functions based upon the grouping of the variable actually. Rating wise, we are grouping it. And for those groups, we are finding minimum age. Find the age of youngest Siler with the age greater than 18. Who can vote? The question is actually. So, eligible to vote means age is greater than or equal to 18 for each rating with at least 2 such Silers. That means we have to find out rating as well as the minimum age. But not all groups. Previous query actually speaking. But it's not for all groups. Which groups we want to consider? We have to consider all sailors who able to vote. That means whose age is greater than or equal to 18. And what is another one? Each rating should have minimum 2 numbers. Otherwise, don't consider that type of rating. Minimum 2 sailors must be there who are eligible to vote that particular vote, who are having the voting age. For those groups only, we have to find out the minimum age. So, as I explained you earlier, so I am displaying rating as well as the minimum age. We are renaming them as min age from Silas, where what is the first constraint? Age must be considered. So, Silas age is greater than or equal to 18. It was filtered. Only we will consider the group of Silas who are having or who are eligible to vote. Again, from in that particular filtered group, group by S rating, and we are grouping no rating wise we supposed to get the minimum age, so that's why rating level wise we are grouping them. But what are the groups to be considered? Which groups are having minimum 2 members? So that's why having count star is greater than 1. Greater than 1 means 2 stars, or greater than or equal to 2. Both are one and the same. So that's why you observe here, we are filtering first data only for the group of students who, group of the sailors who able to vote them. After that, we are grouping them. On grouping again, we are filtering them. So, where is used to filter original database, original data, and having is used to filter group data. Another query, find the number of reservations for each red board. So, we have to find out the number of reservations means counting the reservations red board. So, let us assume that we are going to find out number of reservations means each BID will reserve certain, no? So that's why red board whoever reserved, those numbers are going to be observed. So BID count star as S count from sailors, boards and reserves. 3 relations to be considered because we have to find out the color is red as well as who reserved for that particular board. So that's a combination we need, but group by BID. So similarly, we will consider another set of schema for our SQL queries only. So to discuss such SQL queries, supplier, parts and the catalog, 3 relation schema was given to us, and these are the queries are there. But here you observe, instead of giving a query, the question is related to views. We defined already, one lecture was done on views. So what is a view? It's a virtual table. View definition is going to be stored most of the time, and whenever we are using, that definition is going to be get executed. So physically it doesn't exist, only it executes or stores logically. So we we discussed about entire view and their constraints and updatable or not, how to create a view, how to destroy a view, everything we discussed in detail. So related to view, this is the relation schema was given to us. What are the queries? Give an example of updatable view involving one relation. Give an example of updatable view involving 2 relations. Give an example of insertable into view that is updatable. That means whenever you are inserted, automatically view also supposed to get updated. Give an example of insertable into view that is not updatable. We defined what is a view, but some of the views are updatable and some of the views are not updatable. Updatable means you can execute insert, delete and update operations on view, or any base relations are undergone any such type of updations, those are going to be reflected in our view also. While defining the view itself, all these options are available to us, we discussed already. So whenever the base tables from where the view is going to be generated, that those tables are known as source tables or base tables. So these updatable views refers to the specify the tables to be updated in data change statements. So when any change is made in your view, data changes, data modifications, it should reflect view. Any view, if you have done, it should reflect your base tables. Any changes have been made in the base tables, it should reflect our views also. So that's why for a view to be updatable, there must be a relationship between the rows and of our view as well as the rows of our base tables. Underlying tables or base tables or source tables, we'll call all of them one and the same. There are also certain other constructs that make view non-updatable. For example, that if you are generating a view which can, because view is going to be created as a result of a query. So if that particular select statement consists of aggregate functions, distinct, group by class, having set operations, some set type of subqueries, that is the subqueries which are written in select statement and some kinds of joins. If these operations are used while creating a view in the subsequent select statement, such type of views are not properly updatable. Even we are trying to do, the updations may not reflect the proper way actually. So that's why related to the first one, a simple one, any view you can create by using a single relation schema without having any aggregate functions. They asked only examples, multiple examples can be there. So it should not contain any aggregate or a group by class or having class, etc. So create a view, just a simple view was given. V1 update consists of part ID, part name and color. This view consists of these three attributes, but it consists of tuples whose parts are going to be having color. Red color parts only we are making it as separate view. So select star from parts where color is equal to red. Star means three attributes only. So these three attributes are automatically transferred to the attribute part ID, part name and the color of the view. But not all tuples. The tuples are filtered. Only red color part tuples are going to be considered for our view V1 underscore update. Second one, if you are going to consider, give an example of an updatable view involving two relations. So we can use two relations, no problem, but those two relations must be joined properly. Okay, such a way we have to consider. And when you are using theta join, etc., in such cases, certain problems may occur. But if natural join, only if the data is not available for us, null will be considered for the attributes for which the data is not available actually. For example, we are creating a view from two relations, parts and catalog. And the view consists of the attributes part ID as well as you are going to have supplier ID, cost as well as part name. So based upon this cost and the respective part details are there, along with that who supplied that particular part. So that's why part ID, SID, that is both are available. So two relations are there. Parts is P, catalog is C. Catalog consists of all details except part ID. Part ID is also available both the catalog as well as for us parts also. So PID, catalog ID and the parts are having CSID common. So you can use that for actually. So we are creating more than one table was generated. And the solution here, so by using two tables here, instead of using PID, SID, if you are having, I may use our color also. Part name is there. Part name is available in our parts only. Okay. And we are having suppliers. Part name is available. Part ID is there. Here, our supplier ID, part ID, and cost is there. So for attribute, that's why we are taking these two tables, parts and catalog, and we are joining them by using a common attribute concept, that is PID of part is equal to PID of catalog. So that's why any updatable view was generated. If any updations have carried out in our base tables, automatically those are reflected. Similarly, any updations you are making, that is updations means insertion, deletion, all these operations, data manipulation operations, those will reflect our base tables also. And another, of course, at the time of creation of view, if you are having some restrictions, then problem may arise there actually. Give an example of insertable into view that is updatable. So you can use any view that can be updatable, but please avoid, as I explained you earlier, group by class as well as aggregate classes, etc., which cannot be updatable the data. For example, if I am taking aggregation increased by 2 means who are those two, we don't know. So I cannot add those details in my aggregate number of, let us assume that number of parts are increased by 2. So that means count of PID is incremented. Let us assume that I am updating my view. But how these updations will reflect our base tables, because aggregate values were updated here. According to that, the tuples must be generated in our insert, or some insertions must carried out in our base tables, which is not possible. So that's why that was explained in the fourth example, not updatable. So just you observe, I'm creating a view with the supplier ID and average cost, how much they supplied, whatever the item supplied, supplied that their average cost of that is the average cost by each supplier will be considered. So what is the subquery? Select SID average cost from catalog group by SID. Fine, this view will be generated, but it cannot be updatable. Why? Because, for example, if I'm increasing my average cost, what is this average cost computed value? Based upon that, can I make any changes in my base table catalog? No, automatically it cannot be updated because average cost increase means some tuples related to the respective supplier ID was included. But how to include, how much or what supposed to be included, these things are not properly considered. Such views are not updatable. These views are only for viewing the data but not updatable. Updatable means it cannot be inserted or it cannot be, modified, delete, etc. The next query here, solve the query. This is a two relations are there, student and marks consist of grade number and mark. First student is having name of the student, gender, address, city and class name also, and marks consist of grade number, subject 1, 2, 3, total and percentage. Simple queries are there. Display the student of FIBCA and TYBCA. So what is this FIBCA and TYBCA means here related to the class. So I have to check display the student of that means display the student of FIBCA means select star from student where class is equal to FIBCA or class is equal to AND operator. Sorry, here in the query it was given as an AND operator. So instead of OR you can use AND. Second, display the marks of students whose grade number is greater than 100. So marks of the student means it will be taken from the marks relation directly because grade number is also available in the marks and marks are also available. Marks details are also available. So that's why the query can be based on grade number. So select star from marks where grade number is greater than 100. Simple query. Count number of girls. Number of girls means in the student we have, gender is there. So we have to find out first. Number of girls means counting. So that's why we need select count star number of girls from the student group by gender having F. Or you can use another query also. A simple query can be written. This can be replaced with select count star from student where gender is equal to simple query. Need not use all these things also. Gender is equal to F. That means I am filtering the data. Gender is equal to F only we are taking. Those tuples are counted. That means number of girls are available. So instead of using this group by having directly, you can write like this. Simple one. Count the number of first class students in TYBCA. Number of first class students. I am assuming first class means whose percentage is greater than or equal to 60. Those are considered as a first class student. So where is this percentage is available in marks? So that's why select count star number of first class students from marks where percent is greater than 60. First we are filtering. Percent greater than or equal to 60, only those tuples are taken from the marks. We are counting those tuples. That is count star. So another question is there. Another question, consider this is based upon our candidate keys. So consider a relation schema R of A, B, C, D, E, H on which the following functional dependencies are whole. A determines B, BC determines D, E determines C, D determines A. Write candidate keys. So candidate keys means any set of attributes determines all attributes of the relation, then it is a candidate key. Determines means, for example, we will find out the closure. What is closure? Closure of a set means, for example, if the set of FDs are F plus is defined as a closure of functional dependencies, which consists of all set of FDs derived from these FDs. We discussed in detail about this closure of attribute, closure of set F functional dependencies, etc. So from this set, by using some inference rules, Armstrong axioms and some inference rules, by using these rules, if you are able to generate all possible functional dependencies, that set is known as, there is no new FD can be generated further. In such a way, you can generate all FDs from the given set of FDs, holds on F, holds on our relation R, then we can say that is known as a closure of. Similarly, attribute closure also can. Attribute closure means, for example, A determines B and D determines A determines B, B determines D means A determines D. New one. That means A determines BD both. Like that, if you are going to get, we will get the closure of attribute set AEH, BEH, DH. These three closures will be entire relation schema R. By applying inference rules, the closure of AEH, BEH, DH, we will get the set of all attributes because the trivial dependencies are there. No, AEH determines AEH. So other than that, I suppose to consider AEH should determine our AEH over no BCD. So A should be determined B, BCD determine D, D determines A, and based upon this, by applying inference rules, transitivity and associativity as well as union rule, by applying this, we will get attribute closure is going to be identified. So attribute closure is this one, so that these are all keys. So AEH, BH and DH are candidate keys. Using the given set of functional dependencies, looking at the dependent attributes, if you are seeing that B is dependent, you observe by given set of functional, D is dependent, C is dependent, A is also dependent. So B, C, A, D are dependent. You observe those are dependent on some other thing. A determines B means B is dependent on A. So that's why these two are not dependent. So combination of these two and any attribute combination of these two attributes will be a candidate key. Always remember that. Okay, EHR candidate keys anyway, because EHR doesn't depend upon any attribute means those are candidate keys. So associated with the EH, what are the other attributes can be associated? A can be associated, B can be associated, C can be associated, D can be associated. But among these things, A, B, D are okay. C is not possible. Why? Because here E determines C. E determines C. So that's why C depends upon A. So C cannot be added here. So based upon this, EH can be joined with or combined with E and H are dependent on, not dependent on any of them. So they must be part of any candidate key. So only the option is D, as we see that if D adding A, B or D to EH do form a candidate key. So that's why by using this, C cannot be formed actually. So that's why AEH, BEH, DH are candidate keys. This can be written in a elaborative manner because we have to calculate this attribute closure by applying recursively or repeatedly inference rules and identify attribute closure of A, B, C, D, like that, AE, EH and AEH, BEH, etc. Right? Attribute closure means the set of attributes determines the entire relation, then it is an attribute closure. Coming to the next question, question number 7. Consider the following relational schema of library. We are having book collection. Two relations are there, and the collection consists of title, author, catalog number, and book consists of title, author, catalog number, published year, price, etc. The following are the functional dependencies holds on these two relations. Title, author determines catalog. Okay. And catalog number determines title and author. Catalog number determines publisher and year also. These two also. And publisher, title, year. Publisher, title, year. That means publisher, title, year. These two are going to be determining price. So what are the keys first? First you have to find out the keys, but you can assume that author title is the key of both. Author title, this is the key, this is the key. Key attribute of these two relations. What I supposed to consider? Apply the appropriate normal form for the book as well as the collection. Two relations. By considering the two relations, what is the first normal form? First normal form means all attributes must be atomic, indivisible. This satisfies. So your book relation is 1NF and your collection relation is also 1NF. First normal form, both are evident. What is second normal form? Second normal form means all non-key attributes must be fully functionally dependent on key attributes. All non-key attributes. All non-key attributes means here these are the non-key attributes. These must be determined from the both the title author. So you observe title author determines catalog number and catalog number determines the title author publisher year here. And third FD is there here. Publisher title year determines the price. That is part. So in the first case here, partial dependencies exist in book, and in the collection, partial title author determines catalog name. It here fully functionally dependent, FFD. But here partial dependencies exist. Partial dependencies exist in the book relation scheme. So that's why book is not at all in the even second normal form. We can convert into second normal form, but collection is having its second normal form. So book is in second normal form and collection is third normal form. The table collection will be considered here, and book cannot be in second normal form because partial dependencies still exist. So we can say that book is in 1NF and collection is in 3NF. 3NF why? Because partial dependencies doesn't exist, as well as because title doesn't determine, because fully functional dependencies exist. And third one is transitive dependency. Related to this, no transitive dependencies are there. So that's why collection is in 3NF, but book is only in 1NF. Even second NF is also not possible because partial dependencies exist. Partial dependency means here title author. That means you are going to consider the title author determines catalog means part. Entire key is determine the catalog number. But publisher year price, if you are coming back, catalog number determines author, publisher and year, which is a transitive dependency. So that's why it can be considered as a book can be in 1NF and the second one is in 3NF. Coming to the next question, relation schema. A relation schema was given to us, A, B, C, D, and the set of dependencies are given. A determines B, D determines C determines D. And find whether the decomposition R into R1 and R2 belongs to one of dependency preserving and lossless join. Now, this is divided. What is our relation? Our relation schema is A, B, C, D. It is decomposed into two subrelations. What are the subrelations? A comma B is one subrelation. C comma D is in another subrelation. What are the functional dependencies? A determines B and C determines D. When we are decomposing, AB holds on the first subrelation, CD holds on the second subrelation. AB holds on the, because AB both exist in the first subrelation, it holds on the first subrelation, and CD holds on the second sub. That means when you are decomposing the relation into subrelations or relation schema, those relations are dependency preserving. That is, R1, R2 both are satisfying the dependency preserving property. What about lossless join? But not lossless join. Why? That means when we need to check the parameters lossless join and dependency preservation, lossless join means R1 and as well as R2 should be intersection of R1 and R2 should be equivalent to either R1 or R2. That means here R1 of AB, R2 of CD determines R1 of AB. That is, the intersection of these two is going to be null anyway. So that is R1 of AB and R2 of CD determines R1 AB. And also R1 of AB and R2 of CD determines R1 of CD. This satisfies here. But functional dependencies are going to be here. So that's why the statement above is not possible as R1 because determining to the entire ABCD is not at all lossless join. So that means it's a lossy join decomposition here. But as I explained you, dependency preservation is a holds good here. Because one dependency holds on first subrelation, another dependency on second subrelation. So either of them is determining our ABCD. So it holds good. So the dependency relationship, combination of these two and the operator doesn't hold as the dependencies are individual there. So that's why it's not lossless join decomposition, but it is dependency preserving property holds good. Coming to the next question, another question we are discussing, question number 12 in the question bank. Suppose that we decompose the schema R of A, B, C, D, E into two subrelations. Show that this decomposition is lossless join decomposition if the following set of functional dependencies holds. So how we are decomposing? We are decomposing A, B, C, D. This is my original relation. So A, B, C, D, E, these are the attributes. And this is decomposed into R1 of A, B, C, A, B, C, and R2 of C, A, D, E, A, D, E. Two subrelations. So the total entire ABCD subrelation is here we are considering here. The total entire ABC relation is R is decomposed into as R1 of ABC and R2 of ADE. So what are the set of dependencies holds? A determines BC, CD determines E, B determines D, and E determines A. What we need to prove? This decomposition is a lossless join decomposition. Lossless join decomposition means R1, R2 is a lossless join decomposition if R1 intersection R2 determines R1 or R1 intersection R2 determines R2. If either of these two conditions satisfies, then we can say it is a lossless join decomposition. What is R1 intersection R2? R1 intersection R2 is, what is R1 intersection R2? R1 intersection R2 is intersection of R1 and R2 is A. So what I supposed to consider? A determines R1 means ABC or A determines R2 means ADE. If either of these two functional dependencies are holds good, then we can say our decomposition is a lossless join decomposition. That is, if A is a candidate key, then it's okay for us. In other words, A is a candidate key, R1 intersection R2 determines R1. You observe here, A determines, you are going to consider, we are supposed to get ABC. A determines A automatically, first FD. It is a trivial FD. And A determines BC, first FD. With this, if you are using union operator, A determines ABC. So this is holds good, right? So that's why when we are considering this here, in this case, A intersection R1 intersection R2 determines R1 holds good. So then the lossless joint decomposition is, this decomposition is considered as a lossless joint decomposition. So A determines A ABC, or A determines ADE must be satisfied. So first we are taking a relation schema and we are taking subrelations. What we are considering? Union intersection of the two subrelations, R1 intersection R2. What is R1 intersection R2? R1 is ABC, R2 is ADE. So what is R1 intersection R2? R1 intersection R2 is A. This is exist in both relations. So what is lossless joint decomposition definition? R1 intersection R2 must be determine R1. R1 intersection R2 must determine R2. Either of them satisfies, then the decomposition is lossless. So coming back to us, our case, that means A should determine R1, A should determine R2. Either of them must satisfy. So coming to the first set of FDs given, A determines BC, A determines A is trivial dependency. So combination of these two gives us A determines ABC. That means our A determines R1, that is R1 intersection R2 determines R1 satisfies. So it is a lossless joint decomposition. Another question. Suppose that we have the following three tuples in legal instance of relation schema S with three attributes ABC. So A, B, C, three attributes. What are the tuples? 1, 2, 3 and 4, 2, 3, 5, 3, 3. These are the tuples. This is the relation schema and this is the instance of relation schema. Okay. Which of the following dependencies can you infer does not hold over schema? Does not hold over, right? A determines B. If any equal A are there, B equal. So no equality. So this is trivial now. B determines D. B 2 equal. Then 3 is there. So that's why B determines C holds. First one holds. Third one also hold. So which does not hold? Does not BC. BC means combination. Sorry, 2, 3, 2, 3, 3, 3. BC values. 2, 3, 2, 3 are equal. 2, 3 determines 1. And 2, 3 determines 4. So this is not hold because left side equal means if the functional dependency exists, right side also must equal. BC determines A means B, C are equal. Then A also must have equal values, which doesn't have here. So that's why the second FD doesn't hold. That is BC determines A means here we are getting from these tuples 2, 3 determines 1, 2, 3 determines 4 and 3, 3 determines 5. So left side these two are equal but these two are not equal. So this FD doesn't hold actually. Okay. So by using various set of relation schemas, we able to write some queries by using our SQL structure and SQL statements, as well as we discussed some of the problems related to our lossless joint decomposition, as well as our entire combination of the functional dependencies and normal forms. While discussing this normalization and functional dependencies, we need to find out the candidate keys means we have to find the attribute closure and F closure set of functional dependencies closure, then we need to find out candidate keys exist or not. Similarly, if you would like to define whether the decomposition is a proper decomposition or not, two characteristics we have to check: lossless join as well as the dependency preservation. Lossless join means intersection of the subrelations must determine either of the any of the relation subrelation. Then we can say it is a lossless join decomposition. Okay. Thanks for watching this video.
Like, share and subscribe. Hit the bell icon for more updates.